Hi, in this video, we want to take a look at measures of association when we're analyzing our data. All right, so measures of associations are techniques that we use to determine from a math point of view, is there a relationship between two variables? So for example, we could think that there might be a relationship between temperature outside, they'll say the median temperature of the day, and ice cream sales, right? So we would expect to see, as it gets hotter, we would see more ice cream sales. We would expect to see, as it gets cooler, we would see less ice cream sales. So there's an association there. So what we want to do, we want to be able to take data and numerically describe, is there a relationship, yes or no, and how strong is that relationship between the variables? So measures of association are used in statistics to quantify the strength and direction of the relationship between the two variables. All right, so direction, imagine the situation that we're talking about, here with the temperature and ice cream sales, they both go up. If one goes up, we expect to see the other one going up, because if ice cream sales went up, we would expect to see, well, more than likely, it was a warmer day, so I would expect to see higher temperatures. Now, it does not mean there's a causation there, but if I was just looking at my data, not knowing anything else about it, that's what I would expect to see. There's other situations where if one goes down, we expect the other to go up. When one goes up, the other goes down. So measures of association allow us to determine if there's a significant association between the variables and to what extent they are related. By calculating measures of association, we can determine if changes in one variable are associated with changes in another. This information can be used to make predictions and draw conclusions about the relationship between variables. So here are 5 common uses for measures of association in research. First one is to investigate the relationship between 2 or more variables. The second, determine the strength and direction of the relationship between variables. Test hypotheses about the relationship between the variables. Predict the value of one variable based on the value of another. And identify patterns and trends in the data. Overall, measures of association are valuable statistical tools that help researchers to better understand the relationship between 2 variables and to draw meaningful conclusions from the data. All right, so now let's get into some particular measures of association. First one, and this is by far the most common, most well-known, this is Pearson's correlation coefficient. So if you hear just correlation, we're talking about Pearson's correlation coefficient. There are multiple forms, multiple ways to measure correlation. If you hear the word correlation, classically, we're talking about Pearson's correlation. All right, this measure is a linear relationship between 2 continuous variables. It ranges from -1 to 1, or -1 indicates perfect negative correlation, +1 indicates a perfect positive correlation, and 0 indicates no correlation at all. This measure of association is appropriate when both variables being analyzed are continuous and follow a roughly linear relationship. Pearson's correlation coefficient is sensitive to outliers and assumes that the relationship between the variables is linear. All right, so suppose that we want to investigate the relationship between a person's age and their income. Both variables are continuous, and we expect the relationship between the two to be linear. In this case, we would use Pearson's correlation coefficient to measure the strength and direction of the relationship. All right, so now let's look at some R code, just showing the example. So here we have age as a variable. Here we have income, and this is all just randomly generated data. Now, to do what's next, I'm going to go ahead and put everything into a data frame to put all my variables together into one neat little package. And now I'm going to visualize it. And so here I'm using ggplot, and Pearson's correlation measures how well do the dots line up with a straight line. That's really a good way to think about it. And so here we can see that there is overall a linear trend when I look at just the dots, but it's not a perfect linear trend. If it was perfect, all of the dots would be on that blue line. All right, so let's quantify how well is this adhering to a straight line. So I'll just use the correlation function in R, COR. The default setting in the correlation function is Pearson's correlation. And we can see that this is a 0.84 correlation. All right, that's actually pretty good, pretty strong. This would be a relationship that I would want to use for modeling if I was doing this at work. Now, the next one is Spearman's rank correlation coefficient. This is a non-parametric measure of the relationship between two variables that can be applied to both continuous and ordinal data. It assesses the monotonic relationship between two variables, which means that as one variable increases, the other variable either increases or decreases. All right, so there's some things going on here. Spearman's rank correlation coefficient, focused in on the word rank. Roughly speaking, not 100%, but roughly speaking, Spearman's rank correlation is where I convert my data to the rank, as in like first for smallest, second for second smallest, third for third smallest, and so on. And then I run Pearson's correlation on the rank of my data. All right, so this is not exactly 100% correct, but it's a good way to think about it. The reason why what I just said is incorrect is because of ties. Now, something that's happening also is that this picks up monotonic relationship. So it can happen mathematically that two variables, as one increases, the other one also increases, but it doesn't form a straight line when I plot it. And so here, this is a little bit more flexible on picking up the relationship between two variables. So here it's trying to find, is there a monotonic relationship between the two variables? All right, so this measure of association is appropriate when both variables being analyzed are ordinal or continuous, but the relationship between the variables is not linear. All right, so if I have a linear relationship, or I want it to be a linear relationship, I'm going to use Pearson's correlation. If I'm more flexible on the relationship between variables, I'm going to use Spearman's rank correlation coefficient. So remember, Spearman's correlation is non-parametric. So it does not assume a specific distribution for the variables. And this is less sensitive to outliers than Pearson's correlation coefficient. All right, so let's run through an example. Suppose that we want to investigate the relationship between a person's rank in a race and their heart rate. Rank is ordinal and heart rate is continuous, but we do not expect a linear relationship between the two. We expect that a person's rank that as a person's rank improves, the heart rate will decrease. In this case, we would use Spearman's correlation to measure the strength and direction of the relationship. All right, so here is their rank in the event, and notice I have duplicates. I did that intentionally. Duplicate values would indicate a tie in this situation for the foot race. I did it this way to have a specific result in the upcoming plots. Now here is the heart rate of each individual. I'm putting everything into a data frame to make everything nice and neat when I work with it. And so now I plot the actual value. And so you'll notice that the curve here is not a straight line. And I'm trying to pick up, is there a monotonic relationship between these? So as one variable increases, I want to see the other one increase also, or there to be an association that I'm looking for of this type. And I can go ahead and calculate the correlation. So Spearman's correlation is 0.94. This is pretty good. I would definitely want to use this if I was working on a model at work. Now, the next one is Kendall's tau. And my professor called this the correspondence between the variables. This is another non-parametric measure of the relationship between two variables that can be applied to both continuous and ordinal data. Like Spearman's rank correlation coefficient, it measures the strength of a monotonic relationship between two variables. This measure is appropriate when both variables being analyzed are ordinal or continuous, but the relationship between the two are not linear. So if I have a nonlinear relationship, or I believe there is a nonlinear relationship, I'm probably going to want to use Spearman's or Kendall's. My personal experience is that Kendall's usually takes a little bit longer to compute, so I usually use Spearman's more often. Kendall's tau is also a non-parametric measure and is similar to Spearman's coefficient in terms of sensitivity to outliers. All right, so now let's run through an example. Suppose we want to investigate the relationship between the level of education attained, that's ordinal, and the income level for a group of people. All right, both variables are, are ordinal, and we expect the relationship to be monotonic, but not necessarily linear. In this case, we would use Kendall's tau to measure the strength and direction of the relationship. And so here, to run through this, there's a typo in the paragraph I had. Income would be continuous for this. So to plot this, here I have high school. You can see that the box plot says the central tendency is around 40,000 for this fake data. College is around 50,000 for this fake data. And graduate is around 55, or a little bit less than 55,000. All right, but we can see that there is an increasing trend overall, but it's not a perfect increasing trend. Kendall's tau gives us a 0.43. So it's positive. So we see that there is a, as one goes up, we expect the other one to go up also, but it's not as strong of a relationship as what we would see elsewhere. All right, the next one we want to talk about is the contingency coefficient. Now here, we're going into purely categorical data. This measures an association between two categorical variables. It ranges from 0 to 1, where 0 indicates no association, and 1 indicates a perfect association. This measure of association is appropriate when both variables being analyzed are categorical. The contingency coefficient is often used to measure the association between nominal variables, but it can also be used for ordinal variables also. So suppose we want to investigate a relationship between a person's gender and their political party affiliation. Both variables are categorical, and we want to measure the strength and direction of the relationship between the two. In this case, we would use the, okay, so this is a typo I should have dropped. I should not have the word direction on that because there's no direction aspect on this one. But we do want to measure the strength of the association. So here I'm going to take some fake data. Here's the gender. Here's the party. And now, a little bit different than what I did before, I'm going to create a contingency table for this. Now, I intentionally chose gender and party because they have a different number of levels. So gender, male, female, party, Democrat, Republican, and independent is in there. And so now I have a 2x3 contingency table. Now this is fake data, so the numbers don't really mean anything. To be able to plot this visually, I'm going to go ahead and convert this to a data frame. And then we're going to go ahead and plot it. So blue means Democrat, red means Republican, green is independent. And so we can see that there is something going on, according to this data set, because we see that there are no Republicans in the female column. We can see that there are no Democrats in the male column. All right, so this is fake data. This is not real data, but this gives us an idea of how to interpret if I see, no level appearing with another level or very, very minimal count. That's an indication of something going on between the two nominal variables. So now let's go ahead and calculate the contingency coefficient. All right, so my internet research is that the best way to approach this is to use the VCD package, association stats. And so here we can get our contingency coefficient of 0.65. Here's Cramer's V, which we will talk about in a moment, of 0.86. And so here, this is Pearson's chi-squared test statistic. Here is the p-value. So we see that there is statistically something, or there's statistical significance on this hypothesis test. We can also do a likelihood ratio test, depending on which one you feel more comfortable with. My experience is that Pearson's chi-square test, more people are familiar with it, so that's the one I will choose to use most of the time. Now the phi coefficient, this is a measure of the association between two dichotomous variables. So here, when we say dichotomous, there's two levels, such as 0, 1, yes, no, male, female, on, off. It is similar to the contingency coefficient, but it is specifically used for binary data. The phi coefficient is a special case of the contingency coefficient. So suppose that we want to investigate the relationship between a person's smoking status, that is smoker or non-smoker, and their risk of developing lung cancer, yes or no. Both variables are dichotomous, and we want to measure the strength of the relationship between the two. In this case, we would want to use the phi coefficient to measure the strength of the association. And so here I have some fake data. Smoking, here I have some fake data for lung cancer. So a 1 indicates that they are a smoker, 0 indicates they are a non-smoker, a 1 indicates that they have lung cancer, a 0 indicates that they don't. And I'm going to create a table. Here's that table. Now we'll notice that on this fake dummy data set, we have perfect association from a data point of view, that every time they're a smoker, they have lung cancer. Every time they're a non-smoker, they don't have lung cancer. All right, so here, this is a very extreme result, and this gives us a feel for what's going on. So now we see phi coefficient of 1. We see a contingency coefficient of 0.7 and Kramer's V of 1. All right, so this is indicating a very strong result, but realize that's a very small data set. Small data set, can I really trust it on that level? Now, there is something going on, but is it as strong as it appears to be? The contingency coefficient picked up that it's too small of data for us to believe it's a strong result. It's only 10 data points. So here, I would use the contingency coefficient to report this one instead of the phi coefficient. It's a perfect relationship off the data, but it's very, very small. So I personally would back off of phi coefficient for this particular case. If I had a larger data set, I would 100% go with it. Now the next one, this is the one for the categorical and dichotomous data. This is the one that I've used the most at work, Kramer's V. This is another measure of the association between two categorical variables. It is similar to the contingency coefficient, but it takes into account the number of categories for each variable. I personally use this for monitoring predictive models that run monthly at work and checking to see if the distribution of my output changes over time. That's where I personally have used this. This measure of association is appropriate when both variables being analyzed are categorical, but there are more than two categories for each variable. Kramer's V takes into account the number of categories for each variable and is a good measure of association when the contingency table is large. Now, suppose we want to investigate the relationship between a person's education level, high school, college, or graduate school, and their profession, doctor, lawyer, engineer, teacher, etc. Education level is ordinal, while profession is categorical, and there are more than two levels for each of these. In this case, we would use Kramer's V to measure the strength of the association, which will be taking into account the number of categories for each variable. All right, so let's go ahead and generate some fake data to work with. Here's the education level. Now here I'm putting education level as a factor. That way, as I run through this, things are ordered in the correct manner. Here is the profession. Notice that there is no ordering on it. And so R is going to present things in alphabetical order. I create my table. And so here we can see, here's my contingency table. And now I can get my Kramer's V statistic off there. So 0.65, where we know that 0 is no relationship, 1 is a perfect relationship for this type of measure. All right, so it's not as strong as I would have expected. Once again, this is a smaller data set. We, you know, I would have expected it to have been stronger with things like doctor. Doctor would definitely be in the graduate school level, 100%. Teacher in the state of Florida, teachers are required to have completed, college, to have a bachelor's degree. Therefore, I think that, this is not truly picking up what's truly going on in real life. So that's just my assessment. It's my fake data. All right. So in conclusion, measures of association are statistical tools used to quantify the strength and direction of the relationship between two variables. There are many measures of association, each of which is appropriate for different types of variables and research questions. For example, Pearson's correlation coefficient is used to measure the linear relationship between two continuous variables, while the contingency coefficient is used to measure the association between two categorical variables. By calculating measures of association, researchers can determine the extent to which two variables are related and make predictions about one variable based on observing the other. I do that all the time at work with predictive analytics. Measures of association are commonly used to research to investigate relationships between variables and to draw conclusions about the patterns and trends in the data. However, it is important to remember that measures of association only provide information about the strength and direction of the relationship between two variables. They do not prove causation, and other factors may be responsible for the observed relationship. So correlation does not mean causation. Therefore, it is important to use caution when interpreting measures of association and to consider other possible explanations for the observed patterns in the data. All right, here is the homework for this section. All right, well, that's all I've got for you. Life is short. Do math.